Thank you. How are you doing, Dominic?
I'm pretty well. How are you, Uri?
I'm a little bit under the weather, but I'm really excited to be here and see so many familiar faces. I can see Robert, Tracy, Deborah, and many other friends here, so it really excites me. This reminds me, hey there, this reminds me last year in Angular Connect, do you remember that? In Asim's talk?
Yeah, we were sitting in the front row. I remember that pretty well. And it was Angular Connect. And Asim was talking about how to AI in JavaScript. And Asim is a very nice guy and very funny. So maybe you know one of his projects, which is the Emojifier. I don't know if you know it, but it's a very fun artificial intelligence machine learning
It was
problem.
hilarious.
It's actually nice. It finds some emoji and puts it on your face. It's pretty cool.
Yeah, but I think he also showed us this concept where we would just write a few words and that would generate an app based on the text that he wrote. That was pretty inspiring.
Oh, yeah. So I think without Asim, we wouldn't be on this stage. So we really want to thank Asim for this, for inspiring us to talk about this. So thank you very much, Asim.
Thank you, Asim. So we sat and after his talk, we sat and we talked about it and we started to brainstorm how could it just showed a concept, it wasn't really working, just the idea. We thought how we could convert this concept into something that we can experiment with. So we tried a few ideas, do you remember?
Right, we had a couple of ideas. First, we were thinking about doing exactly what Asim was showing in his presentation, basically generating code based on the requirements you put into a text area, generating a form. We had also the idea about generating an app by just sketching it on a piece of paper or by, I don't know, on a tablet. We had a couple of ideas, but the problem was that all of those ideas were very abstract. So we actually went with something different, more concrete.
Yeah, we narrowed it down to simply, given the signature of a function, like the name and the parameters, could we automatically predict the function of the body?
What? But that means I just go home and have no job anymore. That's my job. I write code.
Yeah, well, you better
That's
learn
insane.
about machine learning or something so you'll have more job in the future.
All right, cool.
So a few words about ourselves. I mean, Darius already gave a quick introduction, but Dominic, I heard you work for StackBlitz.
I do work for StackBlitz. I'm a freelancer. I'm a software engineer at StackBlitz. Who knows StackBlitz? Yes. It's an awesome online IDE for building web applications. I'm also a trainer and consultant for ThoughtRam, where I do Angular, RxJS trainings pretty much all around the world. I do write some blog posts and do a couple of machine learning projects. Uri, what about you?
Yeah, all around the world, and blog posts is basically a summary of me as well. I'm a part of the Google Developer Expert Program, and I also organize a few local communities back at my home in Israel, like IoT community and JavaScript Israel community. So if you ever visit, you are invited to join. And I think let's start talking about machine learning, what machine learning is.
Right. Machine learning is often perceived as very difficult, very exclusive for people with a PhD, with a lot of mathematical background, right?
That's not us.
That's not us. Nope. We don't have a PhD. We don't have anything of any of that. So I think in order to understand machine learning, let's just take a look at a couple of examples, right? For instance, machine learning has actually a really big impact on our everyday life. Right? It's used for many things. For instance, it's used for credit card fraud detection. So there's actually a lot of money that we lose because of that fraudulent activities. It's also used for self-driving cars, right? Imagine you can just sit in a car and the car just brings you from point A to point B without even steering the wheel. That's awesome, right?
I can imagine that. Now, I see a data center? Is that a data center here?
It is a data center. So it's a rack of some hard disks. And even there, machine learning is used to automatically cool these data centers to save some energy. So it's really great even for the environment, which is pretty cool.
Wow, I didn't know that. That's pretty amazing. So how do we do this? Like, is it a special programming language or library? How
That's a great question. So in order to understand that, I would like to take a look at a traditional computer program. This is typically what we would write. We're very familiar to this, and our goal is we have this email, and our goal is to classify this email to be spam or no spam. And the email says how to be a millionaire in 4 weeks.
4 weeks.
In 4 weeks. We all know that's not going to happen unless you have the $1 million idea. But what we would do traditionally is we would chain these rules, right? We have these if-then statements, and we just chain them, concatenate them to build up this almost like a rule-based system. But this is pretty error-prone and very deterministic, and life is not always that deterministic.
Also sounds really tedious to write all of this. So
Exactly.
how would you go about that with machine learning?
Right. Machine learning takes a different approach here. And the most important ingredient for machine learning is data. So we have to understand the data set, the underlying data. So we would have a data set, and that data set that contains set of emails and the label. And this label says if this particular email is spam or if it's no spam.
So basically, you are giving it just a lot of examples, and then there is this classify and optimize, which are just some kind of magic black box that spits out the program at you. Is that?
Yeah, it's like an algorithm that you feed in data, and it's trying to classify every single example in this data set. And then based on whatever comes out, we basically tune some internal things, some internal parameters.
All right. So how does it work? Like, it sounds like magic. Can you
Right.
show it to me?
Let's zoom in a little bit. And what's most commonly used, I mean, there's many different ways in order to achieve artificial intelligence by using machine learning. And there's different algorithms, and one of the most commonly used algorithms or techniques is neural networks.
Neural networks.
Exactly, neural networks.
All right.
We all know in our brain we have these neurons, right? And without these neurons, we wouldn't be able to think, we wouldn't be able to speak, we wouldn't be able to produce code. So these things are basically making us what we are, smart. And so we basically take the same concept of a neuron and put it into something we call artificial neuron or perceptron. It's a very simple processing unit, and we zoom in, right? It takes some inputs and it does some calculations. So it's really just additions and multiplications. Of course, there's a little bit more to this, but because this is very oversimplified, but that's what it is. Does some calculations and then spits out a number.
Basically, machine learning is just multiplying and adding numbers, like a calculator?
Pretty much that.
How does that learn, though?
That's a very good question. And it learns by, well, it spits out 24.4. This could be, let's say, the house price of, I don't know, a house in Copenhagen, right? Which is very cheap.
Very cheap.
Very cheap. But just as an example, we know that the price is even lower. It's 15, so it's a very cheap house.
Cheaper than a dinner.
Yeah, it's cheaper than a dinner. You can buy houses everywhere, very cheap. So we would basically calculate the difference between what the neuron predicts and the actual ground value, the true value, the expected, what we know is true. And there's the error, and based on this error, we would basically just tune some numbers, right? You can see these yellow numbers. We call those weights. And we just simply decrease them, decrease them, increase them, and that's what the learning is all about. It's about tuning numbers.
So, yeah, I see. Basically, machine learning is just an algorithm that figures out the optimal numbers to get the desired output. And then you can do it the same with the emails. Let's say 1 would be spam, 0 would be no spam, and it would just feed it the data and update all these weights, the numbers inside, until it spits out the correct output for all the spam emails.
That's right.
And the non-spam.
Of course, it uses some kind of algorithm, so it's not just randomly tuning these parameters, but we don't have to dive into all those details.
Okay, so that sounds pretty simple, just adding and multiplying numbers and tuning, but how this simple thing can tell a dog from a cat?
Right. Just having one of these simple units is not enough. We actually have to take a whole bunch of these processing units and then just concatenate, connect them together, and then we would end up with something that we call neural network. Right? It's a network that is made up of all these processing units, and if you connect them, you can solve more complex problems.
Okay, so basically connecting a lot of simple computational units, but it's still just numbers, adding and multiplying and tuning, but on a very large scale.
Exactly. At the end of the day, it's just numbers.
Sounds exciting. How do I apply this to our question?
Great question. So remember, our goal is really to predict function bodies based on their signature.
Right.
So the idea, I see you're very excited about this. So the idea is here, you can see that's our function. That could be one example of our data set, right? Remember, we need to have a very large data set. So we would have this function, and then we have some kind of model. That's what we need to create.
Figure out, yeah.
What we need to figure out. That's the big question mark still. We have 2 question marks. But we have some kind of signature. We feed it into the model. Now the question is, what do we want it to predict? Well, the idea is to predict always the next token. We want it to predict the function signature. So the idea is to feed in the signature and let the model figure out basically one token at a time.
So basically, if I get it correctly, we are going to feed it a bunch of functions, and then eventually it learns that all functions starts with a curly brace.
Yep, exactly. So the next step for the same signature would be to predict const. And then the next step would be to predict prefix. So it's always one step at a time. And eventually we have the implementation for this signature.
And then I guess for the const, it would learn that functions usually start with var, let, const, or return if it's a short function.
Exactly. Eventually, yes.
And then it will learn the rules, how based on what we got so far. On partial function, it spits out the next, and we can iteratively create a function given the signature.
Exactly.
Cool.
You hit the nail on the head.
Okay. Thank you. So yeah, tell me more about the machine learning approach, because that's what the slide says.
Right, so that's what the slide says. And what we want to show you is a very typical, common approach on how to solve these problems, right? After all, we're like always thinking how, well, I have this problem and I want to solve it somehow. What is the approach? And a very typical approach is to first, remember, get some data. You have to understand the data. You need a very, very large data set in order for these models, these algorithms, to learn from the data and recognize patterns, okay? Then the next step is to clean the data and to pre-process the data. Because after all, what we have is text. And we know that these models, they work with numbers.
Right, so we need to figure a way to convert the text to numbers.
Exactly.
Same with the spam emails and with the cat pictures. Everything has to be numbers at
Everything
the end
has
of
to
the
be
day.
numbers.
Okay.
So then we choose a model. You would think that there's only one model, one solution to rule them all, but that's not the case. There's different models that solve different problems. So we basically have to choose one that solves our particular problem.
I know, we are programmers. We're used to it depends.
It depends, exactly. So the next logical step would be, once we have the model, we would train it on the data we have, and then eventually we would evaluate our model and see how good it is and what the performance is and how good it does.
You know, I think you're missing the most important final step.
What is the next step?
Profit.
Profit. Of course, that's all we want, right? No, it's not. Before we can harvest the grapes, we have to put in some work.
Okay,
right?
so let's get started.
Let's get started. So what is this? Uri, can you tell me a little bit about how do I get the data? I mean, I obviously don't want to sit down and write all these functions myself and create this large data set. What could I do?
I mean, you have a bunch of programmers here.
We have a lot of manpower.
Let's pull out our laptops. But you know what? I got a better idea. I know these guys, they code a lot and they put some of the stuff on GitHub. So we can just look at GitHub and get all the open source code that they and many others create for them from there and use that as our data.
I'm drifting. I just, GitHub, that sounds awesome.
Yes.
Okay, let's do that. So we can do this. We can use GitHub to get all the functions. But how do I get it? Do I have to go online and download all the repos and put all the functions in the data? I'm lazy.
Yeah, you are a programmer. You must be lazy like me.
Right.
So there is a better way, of course. Do you know Google's BigQuery?
BigQuery.
BigQuery.
I can write big queries?
Yes. And basically, BigQuery is a highly scalable data warehouse, or in simple words, it can run really complex SQL queries on large amounts of data really fast. And it can also run it on the entire open source GitHub dataset. So every single file that is open source on GitHub, it can query it.
Impressive. Very impressive. So we end up with a very large data set. It says like 300,024, large number.
Yeah,
very
and it takes 300,000.
We let the machines do the math.
And the
Right.
amazing thing, it takes less than a minute to run this query
Crazy.
and get all the TypeScript files and extract just the functions from there.
Cool. Awesome. Now we have all the data, and I think it's
Is that
pretty
enough?
good. That's not enough.
It's enough.
The next step would be to clean the data, and that makes a big chunk of the work, actually. This is what we have. Uri, can you tell us what we have to do, like to... This is just a function.
Just one.
Right.
We have 300,000 of them, and we need to prepare them to make it easy for the model to learn from them. So we start by doing the first part is just splitting the signature from the body. So the signature is what we give to the model, and the body is what we want it to spit out at the end of the day.
That makes sense.
So we do it for all the functions. And then if you notice inside the function, there is a lot of information that is not really a part of the code structure, like the strings. They have words in English. We don't want the model to have to learn English in order to produce code. That would be a lot more work, right?
But it's probably very useful information, no?
Right. But in order to get preliminary results and get something working, we want to reduce the amount of data that the model has to look at and to learn. We still want a big data set, but we don't want the model to have to learn English in addition to the code structure.
That could be a second step.
What? Yeah, a second step, totally. So we start with a few transformations. For instance, we take all of the argument name and we replace them with a placeholder. So the model doesn't have to learn all the possible argument names. As you said, it could be a second step. And we do the same with all the constants like strings and numbers. Now, if you look at one function, that doesn't make a lot of sense. I mean, we change one string or one identifier name to a different one. It's still something the model has to learn. But if you look across all the functions, suddenly they all have this arg0, id0, id1. So
Reduce the information.
Exactly. Across the entire data set, there will be much less information for the model to look at. And at that point, we can take advantage of the fact we have knowledge about this TypeScript function. We know like the syntax for TypeScript, and we can use the TypeScript compiler to tell us where each part of the program, where each token in the program starts and ends. And we do this using something called AST, the abstract syntax tree. And this allows us to put spaces between each two tokens. So basically, the model doesn't have to figure out that these opening parentheses are a separate part. They are not a part of the function name or the argument name. So again, we work hard to make it simpler for the model to take advantage of the information we already have about the source code. And one more thing we can do to help the model is just to mark the start and the end of the function. Can you think why that would be required? Because
give me a second. So I could imagine that the curly brace is also used in various other places in our code, right? We would use that for blocks in JavaScript, for if statements, for for loops. So to make it a little bit more easier for the model to understand that this is the beginning of the function, we just add these very simple tokens, these symbols. Is that correct?
Exactly. We do everything we can to make the life of the model easier. And that's one more thing. And I think at that point, we already have reduced a lot of the noise that we had in the data and made it much more straightforward for the model to figure things out, like all functions start with curly brace. But, you know, you said it before. We still have it as text, and we need numbers. How do we do that?
Right, that's the second step of cleaning or pre-processing the data. And that actually, well, we want to prepare the model inputs, something that we feed into the model, into the algorithm, into the neural network. And that involves a couple of steps. Let's take a look at every one of these steps one by one. And the first step would be to tokenize the signatures and the implementations. Tokenization is all about chopping up the signature and the implementations into pieces. Like almost you would cut a bread into pieces, right?
Yeah, like we added the spaces, so now it's really easier to chop it into smaller pieces,
Exactly.
building blocks.
We call those tokens, and what we would end up with is something that we call a dictionary, right? We would have so every single token, every single piece has its unique number assigned. So as we can see, function is 1, the number of the function is 2, and so on and so forth.
And do we build a dictionary for each function, or one big dictionary for the entire data set?
For the entire data set, pretty much.
Oh, so that would be huge.
It would be huge, but you could also limit it to only the 5,000 most common tokens. You could there's a couple of ways you can also deal with that.
And then by removing the values of the strings and making placeholders for the identifiers and argument names, now we really reduce the vocabulary.
Yeah,
so the dictionary is still smaller.
Right. But now we only have a dictionary. So remember, we need numbers that we feed into the model. So the next logical step
will
be translate. Exactly. We want to translate the text into a sequence. That's a very straightforward step, actually, because we can, now that we have the dictionary, we can just simply look up every single token we have and then look up its number in the dictionary. And then we would end up with an array of numbers.
Right, and function is like, in this example, it's 1, so it's every single entry will start with the word function, unless it's exported or something, so it's 1.
Right.
And then it also means that we have all the function names in our dictionary, right?
Yep, exactly.
I get it. And what's that add padding thing? Why would we need padding?
Right. The padding is about, because you can probably imagine that we have functions of different size. We have functions with only 1 parameter. You have functions with 2 parameters. And that's problematic for the model. So we want every single input to be of the same size. And that's why we would add padding. In this case, we just simply add zeros to the left. It's like a left padding to make all the inputs of the same length.
Okay, so far the translation to numbers was pretty straightforward. Are we ready to train with this?
Not yet. Now we're creating the inputs and the outputs. That's actually what we train on, right?
Oh, that's what we showed before when we train it to predict the next sequence given what we have so far. Iterative process.
Exactly. It's an iterative process. So we would end up with 2 inputs. Okay, we call them x1 and x2, and our output is called y, typically. And our x1 is the signature, and our x2 is the sequence of previous tokens. Remember that we always predict 1 token at a time. So in the first iteration, we want the model, we feed in start, which is the start symbol, and the output would be the curly brace, right? That's the beginning of the function. We then take that y and append it to our x2. So we would basically always build up this sequence of previous tokens that we have had the model predict.
So basically for each function we are going to prepare this list, and that's the examples we are going to show to the model,
exactly.
Right?
X1, X2 is what we feed in, Y is what we want to get.
And I have a question about the notation. Like, is it usual to call the input X and the output Y when you are working with machine learning?
Yes.
Okay, and we have x1 and x2 because we have like 2 parts of the input.
Right.
Okay, so
you could have multiple features. We call those features.
Cool. So now we have a long arrays of like numbers representing the signature, the sequence, and the output.
Correct.
And are we ready to train?
No. Hold your horses. Super. Okay, so the last step is something, because we have the output, right? Remember that the token is represented as a number. So this means that the curly brace would be, well, it would be a 9, for instance, coming from the dictionary. But the problem with that is that the model would be a little bit confused because we let the model predict this number, the next token, which is a number. And that's problematic because it could potentially learn some kind of hierarchy or order that says, oh, 6 is smaller than 9, and that's actually not the case because those numbers are actually arbitrary.
I see. So because we just chose arbitrary numbers, but as numbers they have like some sort of order or hierarchy between them, then if it sees like start is 8 and then the next token is curly brace 9, it could infer that we are just increasing the number or something like that.
Yeah, that for one. So the idea is to use something for the output called one-hot encoding. So, and the idea is to have the model basically, let's say for this example, our dictionary only has 9 tokens in it. So we would have 9 numbers. And every single value in this array would represent 1 value from the dictionary, 1 single token. And then the idea is, for let's say 9 for the opening curly brace, then we set the last value in this array to 1 and the rest is 0, and that's called one-hot encoding.
So basically, if I get correctly, we don't want the model to look at the value of the number, so we change every number into an array of zeros and ones, and then based on the position of that one in the array, we move the one to represent simple tokens,
Yes.
different tokens.
Right, and this one does not only just represent a one, this is actually a probability, because we would want the model to say, okay, it's in this case, it would be 100% sure that this is the token, and the rest is I'm 0% sure it can't be any of the rest. So it's basically a probability of every single token, how probable it is to be the next token.
Oh, I see. So this way, when we train the model, we can tell the model, hey, this is the reality. Like, given the function signature body we have so far, this is the next token in the real life. Right. But then when it predicts later what would be the next token, it can actually tell us, I think this is more likely to be here. It can give us more information about what it thinks.
Yeah, it's the same for our reasoning. I always say, okay, I'm 80% sure it's this, and I'm 20% sure it's this. That's basically what this is about.
You know, it depends.
Depends.
All right, so I think, yeah, we need to choose a model. How do we do that?
So we wouldn't start from scratch. At least that's what we would recommend to you guys, is to just take a look at very similar problems, right? Try to understand the problem domain and the problem you're trying to solve, and then don't start all the way from scratch. That's going to give you a headache a little bit. So instead, look at similar problems. And a very similar problem to this is, it's part of natural language processing, NLP. Mm-hmm. It's a problem area.
I mean, that's a programming language, but it's still a language.
It's still text.
Created by human beings.
And a very similar problem to this is actually machine translation. Machine translation means Google Translate. We want to translate some kind of sequence, a sentence of, I don't know, Danish into English, for instance, and that's machine translation.
Trivia time. How do you translate good morning to Hebrew?
Now you got me.
I
can't remember from last year Angular Connect.
Okay.
Anyways, we let the machines do that work, so we don't have to learn all the languages. Anyways, and machine translation, at least a few years back, worked in a very naive way, where you basically just simply translate one word into the target language without giving any regard to the grammar or the structure. But that's a problem, right?
Right.
And that's why they came up with something called a sequence-to-sequence model, because you translate your
sequence of tokens, basically.
Exactly, and you want to predict another sequence.
Right.
So, and we can use TensorFlow for this. TensorFlow is a library developed by Google, and I like to think it's used for machine learning. And I like to think it almost like this box of Lego blocks, almost.
Okay,
right?
so you just pick whatever you need. I mean,
yeah.
You find a similar problem, then you copy the implementation of how they solved it and start tweaking it.
Oh yeah, almost like copy and pasting code from Stack Overflow. No, not really.
That's my favorite book. How did you know about that?
Yeah. So we would use TensorFlow and pick building blocks in order to build our model, right? We have a couple of layers. We call those layers, if you remember from the slide earlier, where you have a neural net. And then we would build our model. But again, not from scratch. You would take a look at very similar problems and then try to use very similar models and architectures and then just tweak it, tune some parameters. We don't have to go into all the details here.
Yeah, now they can also copy from us. They have this slide.
Just take this. But anyways, it uses some very specific architecture, which is the encoder-decoder architecture, but I'm going to spare you all the details because you can also look that up later. So now we have our model.
And we need to train it, right?
Exactly.
Like in the gym.
Like in the gym, training our muscles.
Yeah.
Yeah, almost.
How do we do that?
Well, we can do it on our laptop, but most laptops are just not powerful enough for machine learning.
Hey, my laptop is very powerful. Don't you?
Sorry, no offense. It's probably very, very powerful.
Okay.
So anyways, you can do it on your laptop, but, well, you need a lot of power for very complex problems. So there's a solution to this. And you can use Google Colab for this. It's a platform from also Google.
Of course, Google.
Of course. And it's kind of like StackBlitz, which allows you to run code like in the browser without the hassle of installing any libraries. You don't have to worry about any of that. Installing TensorFlow Keras can be really a pain. And instead just use Colab. And the cool thing is you can even run it and train it on a GPU.
Which I don't have. I do have, but not as powerful.
Yeah,
Okay, I get it. And I see it's pretty small, but I see it says here ETA 7 minutes. So it runs in just 7 minutes on the GPU? That's all?
Not quite. It's 7 minutes
Not?
for one iteration, and we typically have many iterations.
Oh, so it could take hours or days to train just the first...
Yeah, but on the CPU it takes weeks sometimes.
I mean, how do you work like that? How do...
Uri, I have a solution for you.
You do?
Yes, I have a solution for you. And you can use the GCP, the Google Cloud Platform, and use something called the TPU.
TPU, what's that?
TensorFlow Processing Unit.
So it's for TensorFlow?
Yes, it's a dedicated hardware specifically made for machine learning, and believe it or not, it is extremely fast.
I can see now it takes 8 seconds per iteration. It's
like it's that fast.
2 orders of magnitude faster than
Lightning
the GPU.
Fast.
So we have like CPU at the bottom, then GPU, and now we have TPU, which makes it reasonable to train large machine learning models.
Exactly. Bottom line is use the cloud. The cloud is our best friend.
Yes. Yes. Cloud emoji. Okay.
Okay, so once we have the model, we would actually evaluate it. There's a lot of information how you can formally validate this and how to use metrics and stuff like that. We're going to spare you the details. And I think the best way to evaluate this on stage is to actually look at a demo.
Yeah, let's
So get out your phones because it's going to be mind-blowing.
I think so.
I hope so.
We don't know. We trained the model and we need to see. So this is a small vanilla, no Angular, no React, no nothing, vanilla script app that basically when I hit submit, it's going to take this function signature, apply all the transformation of tokenizing it and everything we showed you before, and send it to a Python server that runs our model. So are you ready for that, Dominic?
Let me buckle up.
Okay, and I'm submitting, and it takes a few moments for the model to do all the math and come up with an implementation for add. Sometimes it takes more than a moment.
Remember, this is not if-then statements, really. We're not like hard coding this. We're not saying, hey, if it's add, then spit out this. The machine has learned from the data that we're feeding in what add could potentially look like.
I think my machine is tired. Let's try it again. So, are we ready to add 2 numbers a la machine version?
It is always the same with machines.
Yeah, so let me look at the logs. It worked!
What?
That's pretty creative for adding 2 numbers, right? I mean, we don't know what is Flash after doing. It could be adding number, and it's lifting.
Interesting. Very interesting. So because we have a friend, Shai Resnick. You all know Shai Resnick, and we miss him very much. It would be awesome to have him on stage. So let's maybe say we're getting Shai Resnick.
Get her for Shai Resnick. How would that look like?
What is that? I'm very...
The machine is working, and the result is...
Oh!
Trigger next frame. Seriously. It's so unrelated to anything.
And by the way, guys, we couldn't practice this because it's always spitting out different implementations. So, pretty funny. Pretty funny.
I think the most amazing part is that the model actually learned the rules of TypeScript. Like, we never told the model that it should close this parenthesis or this or add a semicolon at the end of the line. It just learned. It's even better than most of the programmers.
Remember. And that is all about tweaking numbers. Very impressive, no? What?
To summarize, first of all, as we have seen, training on the CPU or even setting the environment on your own laptop is time-consuming and tedious. Take advantage of the cloud. It's so much faster, and it really allowed us to train on like 10,000 functions. It was only 10,000 functions, and it still took like 10 seconds per iteration. And Dominic,
Right.
You taught me that.
Don't start from scratch. If you just start with machine learning, just look around on GitHub, try to understand very similar problems, spare the headaches, and just look at very similar architectures and models and start with that. You can always change that, tweak it, add some layers, reduce the number of layers, and all that stuff, but you don't have to start from scratch, okay?
And I think one of the most important lessons here is that pre-processing the data is important. It's something you have to think about, and you have to think about all the knowledge you already have about the data in order for the model to be able to learn efficiently. And we did that by looking at all the knowledge we have about TypeScript, taking out all the information that wasn't relevant for the specific task we had at hand. And you can also do it with your data.
Yeah, so this is almost a discipline. It's called feature engineering, understanding the data and really understanding that and preparing these inputs and knowing what you would want to feed in and what you want to get out. That's a lot of work. You really have to focus on that.
What you have seen now is just the beginning. We just started to work on it. This is an ongoing process, and we are going to continue experimenting with this. And we are going to speak about it next time in Angular Connect in London and show you how we progressed. But you can also be part of it. So the code, the slides, and thank you.
Enjoy your lunch.